Hi, everyone. This is in-class activity or lesson 12A, variation in average rental prices. Airbnb is a website that connects people who are renting out rooms or homes with people looking for accommodations in that area. In this in-class activity, we're going to look at the prices of Airbnb listings under $500 per night in New York City and examine the behavior of sample means prices for random samples of listings. Your first question asks you, the average Airbnb listing price in New York City is $130 per night. Which of the following would be more surprising? A single randomly selected listing price of $200 per night, or an average listing price of $200 per night in a random sample of 25 listings? Explain. Go ahead and pause your video right now and write something down. Welcome back. So here's just one possible way to explain it. It would be more surprising to have an average listing price of $200 per night. This is because to get an individual price of $200, you would just need to obtain a single listing with that price. However, to obtain an average listing price of $200 among 25 listings, you would need listings both above and below $200. It is more unlikely to get several listings above $200 just by chance. Okay, so the activities or objectives for this activity are, you will understand as the sample size increases, the sampling distribution of the sample mean will become closer to the normal distribution. As the sample size increases, variability in the sample mean will decrease. When taking a large number of samples, the mean of the sampling distribution of sample means is equal to the population mean regardless of the sample size. And then you'll be able to determine when the central limit theorem can be applied to means and use the normal approximation to compute probabilities involving sample means. Okay, so in class activities 9B and 9C introduced you to sampling variability. A sampling distribution, remember, is the probability distribution of a sample statistic, such as the sample mean or sample proportion, as it varies from sample to sample. In-class activity 9B introduced you to the sampling distribution of a sample proportion. In this activity, you will explore the sampling distribution of the sample mean for varying sample sizes and discover the central limit as it applies to means. So now the activity asks you to go to the data center MP sampling distribution of the sample means continuous population tool at their Shiny apps. So let me switch over to the screen. And again, hopefully you have this bookmarked already. And this is the data analysis tools. This is the clearinghouse site for these tools. So you can see the various different categories. For this one, they're asking you to go to the Shiny app for sampling distributions and looking for the continuous one. So look at sampling distributions, central limit theorem, sampling distribution of the sample mean, continuous populations. This is the link they have in the activity. You could click on this link. It'll bring you to this app right here, which is called sampling distribution of the sample means, continuous population distributions. Okay, so now what they ask you to do is select the population distribution, real population data, and then choose the New York Airbnb prices. If we go to Airbnb prices, which is right here, you'll see here's the population distribution with the mean of 130 and the standard deviation of 85.1. Okay, so let's sneak back to the lesson. So the first question asks you to examine the population distribution of New York City Airbnb listing prices displayed in the data analysis tool. What is the shape of the distribution? So if you go back again, you'll see that the distribution is skewed to the right. Notice the distribution has a peak and has a tailing off to the right. Again, that's classified or significant of a distribution that's skewed to the right. So the answer is B, skewed to the right. And then it asks you, before we actually get into generating random samples, let's make a few predictions. So after you actually see it in action, you'll know exactly what's going on, but making a few predictions early on. If you were to take 1,000 random samples of sample size 2, New York City Airbnb listings, and calculate the sample mean price for each sample, what shape would you expect the distribution sample means to have? So go ahead and pause the video right now and answer this question. Okay, welcome back. So any answer right now is gonna be okay because this is just a prediction. But as you'll see, we're going to refer to the population. I'll refer to the population distribution as the parent distribution sometimes, and the sampling distribution as the child distribution sometimes. And generally, children look like their parents. So for small sample sizes, like sample size 2, you would expect that the distribution of the sample means would actually look like the population. In this case, the sampling distribution would look to be skewed right as well. So you can write that down. The sampling distribution would expect to be skewed to the right. Just a prediction. And then they say, what if you were to take 1,000 random samples of size 10? So again, increasing the sample size now to 10 and calculate the sample mean price for each sample. What shape would you expect the distribution of sample means to have? Again, take a minute to write something down and pause the video now. Okay, welcome back. So as you're going to notice, and as we do this activity, you're going to see as your sample size increases, the sampling distribution is going to become more normal. So we would expect the sampling distribution to be more normal. Okay. And then it asks you if we did the same experiment, but then increased our sample size to 50 and calculate the sample mean price for each sample, what shape would you expect the distribution of sample means to have? So again, an even larger sample size. The larger your sample size, the more the shape of the expected distribution of sample means is to be normal. So the sampling distribution for the sample means would expect to be even more normal. Okay. So how would you expect the variability in sample mean listing prices to change as the sample size increases? Again, this is just a prediction. Go ahead and write down your prediction now and pause the video for a minute. Okay, welcome back. So again, as you're going to find out, and my prediction is going to be, is that the variability in sample means will decrease as the sample size increases. So the variability in sample means will decrease. Okay, next question says, how would you expect the average sample mean listing prices to change as the sample size increases? Again, go ahead and pause the video now and write down your prediction. Okay, welcome back. So as you're going to find out when we do this activity, the average of the sample mean listing prices is expected to remain the same from no matter what your sample size is. So the average of sample means will remain approximately the same. Okay. So now it's going to ask you to use the tool to generate 1,000 random samples for each of the following sample size. Check the Show Normal Approximation box to overlay a normal distribution on each simulation for each sample size. Check or sketch the graph of the resulting sampling distribution, the sample mean listing prices, include the x-axis label and scale. Use the same X scale for all three plots and the overlaid normal distribution. And then write down the mean of the sampling distribution of the sample mean listing prices. And then write down the standard deviation of the sampling distribution of the sample mean listing prices. So you're going to see we're going to look at for sample size 2, for sample size 10, and for sample size 50. Okay. For sample size 2, 10, and 50, let me go ahead and share my screen again and show you how you're going to do that. Okay. So over here, we want to generate 1,000 random samples for each of the following samples. For size 2, you're going to have to slide the sample size bar over to 2, click on 1,000, and then draw a sample. So here's what the distribution for a sample of size 2 would look like. Notice that the distribution, like we predicted, is a slightly skewed to the right. You're going to do the same thing for sample size 10. So on your sample size bar, you're going to slide it over to 10 and say draw the sample size for 10. And you're going to see for a sample size 10, you're going to have a mean and standard deviation. But again, this distribution, the sampling distribution of the child, is going to be more normal. And then for size 50, you're going to slide over to 50. You're going to see it's going to be even more normal with less of a standard deviation. They did ask you to show the normal approximation for each of those. So if you show normal approximation, it'll draw a approximation above your histogram right there, no matter what size you choose. So if it's 10, there's a slight approximation. If it's 2, a slight approximation. So again, we're doing it for samples of size 1,000. So you can use the clipping tool if you want to clip it and put it into your Word document, or you can just draw a rough sketch on your paper. So I'm going to take this graph and put it into my paper. Okay, so let me stop sharing. So your answer is going to be very close to what I have on my sheet right here. So I did copy and paste for an example where the sample size is 2 with the normal approximation, one where the sample size is 10 with the normal approximation, and one for a sample size of 50 with the normal approximation. Okay, it did ask you to write down the mean and standard deviation of each one of these. So the mean up here for the sample size of 2 is 128. So the mean is 128. And the standard deviation is 58.2. Okay. And then when your sample size is 10, the mean here is 130. And your standard deviation is 26.8. You can notice right away that the means are approximately the same, but the standard deviation is actually decreasing as the sample size is increasing. And then for 50, the mean for this sampling distribution is 130 and a standard deviation of 12. Okay, so now they ask you So compare the results in question 4, your predictions, to question 3. Okay, so the results in question 4 to your predictions from question 3. So part A, as the sample size increases, how does the shape of the sampling distribution of the mean listing prices change? Does this match the pattern you predicted in question 3, parts A, B, and C? And the answer here would be yes. Initially, the distribution in this case, the sampling distribution of the sample means was skewed right, just like the parent, and then became more normal as the sample size increases, and then became more normal as the sample size increases. Okay. And then as the sample size increases, how does the standard deviation of the sampling distribution of the mean listing prices change? Does this match your prediction? Well, again, going back here, when the sample size was 2, the typical deviation was 58.2. Then when the sample size was 10, the standard deviation was only 26.8. And then when the sample size was 50, the standard deviation was only 12. So yes. So as the sample size increases, the standard deviation decreases. So as the sample size increases, the standard deviation decreased. Okay, as the sample size increases, how does the mean of the sampling distribution of the mean listing prices change? Does this match your prediction from question 3, part E? So you can see that when the sample size was 2, the mean was 128. And then when the sample size was 10, the mean was 130. And then when the sample size was 50, the mean was 130. So generally the mean stayed the same. So yes, this matches our prediction. Yes. The mean of your sample means tended to be the same. Okay. So now it says we can calculate the mean of the sample means and the standard deviation of the sample means through simulations as in question 4, or through a mathematical formula. Suppose the mean of the population is mu and the standard deviation of the population is sigma. Then the mean of the sample means is the same as the population mean, mu, but the standard deviation of the sample means decreases with the sample size. Specifically, it can be proven mathematically that the standard deviation of the sample means is equal to the original population deviation sigma divided by the square root of your sample size. So notice as your sample size increases, the standard deviation of the sample means is going to decrease because you're dividing by a larger number. So sampling distribution of the sample mean. When taking many random samples of size n from a population distribution mean mu and a standard deviation sigma, here's your formulas again to summarize. The mean of the distribution of the sample means will be the same mean as the population, and the standard deviation of the distribution of the sample means will equal your population deviation over the square root of your sample size. Okay. So now it says, examine again the population distribution of the New York Airbnb listing prices displayed in the data analysis tool. What are the values of mu and sigma? So if I come back to the screen and share the screen again, you'll see up here that the parent population distribution initially had a mean of 130 and a population deviation of 85.1. So we're going to write that down. So mu in the population was $130. And sigma in the population was $85.10. Okay, let me stop sharing the screen. So I wrote those guys down there. The mean of the population was 130, and the standard deviation of the population was $85.10. Now it says calculate the mean and standard deviation of the sample mean listings for each of the following sample sizes using these mathematical formulas given to you right above. Okay, so for sample size of 2, we would expect the mean of the sample means and just an abbreviation, this is mu of x bar. This is saying the average of your x bars to equal the average of your population of all your x's, mean of all your x's, which is $130 using the formula. You expect the mean of the sample means to equal the mean of the population. And then you expect the standard deviation of the sample means, which we could abbreviate sigma of x bar to equal the deviation of your parent, the deviation of the population divided by your square root of your sample size. So remember, the deviation of your parent was $85.10 divided by the square root of your sample size. In this case, your sample size is 2. If you do this on your calculator, you're going to get an approximation of $60.17 rounded to the nearest penny. We use the same formulas for a sample size of 10. The mean of the sample means, which I'm going to abbreviate mu of x bar. It's saying the average of all your x bars for this particular sample size should equal the average of your population, which is still $130. And the standard deviation of the sample means you expect it to be even smaller because the sample size is bigger. So I'm going to abbreviate that sigma of x bar, which stands for the standard deviation of your sample means is equal to the standard deviation of your parent divided by the square root of your sample size, n, which in this case is going to be 10. So it's $85.10 divided by the square root of 10. Again, if you do this on your calculator and you plug it in, you should get approximately $26.91. So notice the mean, you're expecting the mean of your sample means to be identical, but the standard deviation of the sample means to get even smaller. And then if you go to a sample size of 50, the mean of the sample means, again, we'll call that mu of x bar, is equal to the mean of your parent, which is $130. Again, we're expecting the sample mean to be the mean of the sample means to be the same as the mean of your parent of the population. And the standard deviation of the sample mean, sigma of x bar, to equal the deviation of your parent, the population, divided by the square root of your sample size. But in this case, your sample size is 50. So it's $85.10 divided by the square root of 50. Again, if you plug that in your calculator and you round it off, we expect that to be approximately $12.03. And now they ask you to compare the simulated means, the ones we did on the app, and standard deviation of the mean listing prices from question 4 to these values we just calculated. They seem to be similar, and they should. So if we bring those back, so let's do it for a sample size of 2 first. Let's compare it. So our calculated values for sample size 2 is we expect the mean to be 130 and the standard deviation to be $60.17. You can see our mean turned out to be 128 because, again, this was a simulation. If we did it over and over and over again, on average, we'd expect that mean to be 130. And for this particular simulation, we get a standard deviation of 58 $58.20, which is pretty close to $60.17. Again, this is just one simulation. So if we did this over and over and over again, we'd expect these numbers to, on average, be these numbers. How about for size 10? For size 10, the formulas tell us, and the theory tells us, that the mean should be 130 and have a standard deviation of $26.91 for our sampling distribution. For a sample of size 10, our simulation said the mean was 130 and the standard deviation was $26.80, and 2680 is pretty close to 2691. The mean hit it right on the nose. So again, over the long run, if this is just a single simulation, if I did this over and over and over again, the mean of the sampling distribution should tend to be around 130, the same as the population mean. And the typical deviation for a sample of size 10 should be approximately $26.80. Ours was $26.91, which is not too far away. So that was for sample size 10. What about for a sample size of 50? For a sample size of 50, let me just find my sheet. Here's what the formula tells us. The formula tells us the mean should be 130 and the typical deviation $12.03. For our simulation, for these 1,000 simulations of size 50, our mean was $130 and had a standard deviation of exactly $12. So how does that compare to 130 and 1203? It's within 3 cents. So again, this is a single simulation. Again, if we did this over and over and over for the sample of size 50, these numbers would tend to be what the formulas tell us, 130 and $12.03. So compared to these, do these seem to be similar? Yes. The numbers from the simulation are very close to the values from the formulas. Okay. So now it says in class activity 9C, you saw the central limit theorem at work for sample proportions. In this activity, you just witnessed the central limit theorem at work for sample means. The central limit theorem states that as the sample size gets larger, the distribution of the sample means will become closer to a normal distribution. Excuse me. Combining this with the expressions for the mean and standard deviation of the sample mean results in the sampling distribution of the sample means. When taking many random samples of size n from a population distribution with a mean of mu and a standard deviation of sigma, the mean of the distributions of the sample means is equal to the population mean mu, and the standard deviation of the distribution of the sample means is equal to the population deviation sigma divided by the square root of your sample size. If the population distribution is normal to begin with, then the distribution of the sample means will also follow normal distribution for any sample size. So remember how we said that the parent looks like the child? So if the parent is normal to begin with, then the child will be normal even from a sample of size 1. For sample size 1, the parent and the child will be identical. But as your sample size increases, you're going to notice the standard deviation of the distribution of sample means actually decreases because you divide by the square root of your sample size. However, what happens if the parent is not normal? What if it's skewed left, skewed right, bimodal, uniform, or some other distribution? Well, this is where the central limit theorem is going to kick in. If the population distribution is not normal, the central limit theorem states that the distribution of the sample means will still follow an approximate normal distribution as long as you take a large enough sample size. Standard procedure says the large enough sample size is greater than or equal to a sample of size 30. And the population distribution is not strongly skewed. Okay, so again, if your population is normal to begin with, then these values will apply and your distribution of your sample means will also be normal. If your population is not normal to begin with, then we make the assumption for the central limit theorem that you take a large enough sample size. And again, a large enough sample size is at least 30. You sample at least 30 items from the population, and the population distribution was not strongly skewed to begin with. Excuse me. So now it says, suppose you're planning a vacation to Los Angeles and you'd like to learn more about the distributions of Airbnb listing prices in LA. You take a random sample of 50 LA Airbnb listings. The mean listing price in your sample was $152. Assume the population of LA Airbnb listings had the same mean and standard deviations as that for New York City. You found from question 6. So remember, that was a mean of 130 and a standard deviation of, if I can find it real quick. Pause for a second. Okay, sorry about that. So it says, assume the population of all LA Airbnb listings prices had the same mean and standard deviation as that for NYC, New York City. Remember, this was back when the mean was 130 from the population for NYC, and the standard deviation was $85.10. Okay, use the mean and standard deviation you found in question 7, part C, to calculate the z-score for a sample mean of 152. Write a sentence interpreting this value in the context of the problem. So again, to calculate a z-score, you're going to take the value and minus your mean and divide by your standard deviation. In this case, our value is 152. The mean is really the mean of all of our x's. So the mean is 130. And in question 7, part C, you can find that real quick. Part C. Pause for a second real quick. Again, sorry, there's so many sheets going back and forth. So question was, use the mean and standard deviation you found in question 7, part C to calculate the z-score for a sample mean of 152. Write a sentence interpreting the value in the context of the problem. You're going to take the value minus the mean from part 7, question 7, part C, which is 130, and divide by the standard deviation. But for question 7C, this was for a sample size of 50. This was sigma of x over square root of n. That was $12.03. So if you calculate the z-score, again, this is for a sample of size 50, and that's why we're using the population deviation divided by the square root of our sample size 50 and standard deviation being 1203. We get a z-score of 1.83. So now it asks you to interpret this. It's saying the interpretation, remember, the z-score represents how many deviations you are above the mean. So we're 152, the sample mean of 152 is 1.83 deviations above 130. So we can write something like this: the sample mean listing price of the 50 LA Airbnb listings is 1.83 standard deviations above the mean listing price in New York City. Okay. Now it says, using the normal approximation, find the probability of observing a sample mean listing of 152 or higher from a random sample of 50 listings. So let me pause for a second because we're going to bring up the app. So let me get the app ready. Okay, so welcome back. And I'm going to share the screen. So again, this is our data analysis tool. And you want to find the area under a normal curve. So we're going to go to the distribution, normal distribution. And it's called normal distribution. When you click on that, it'll bring you to this app. Okay. So again, in the data analysis tools in the data center, the normal distribution, which is this app, normal distribution, it'll bring you to this app right here. And you want to find the probability. So you could do one of two things. You can either find the probability in the upper tail above 152 when the mean is 130 and the standard deviation is 12.03. So let's do that first. So if I type in the mean being 130, standard deviation is 12.03, and I want to find the upper tail above the value 152. So you can see it's the value over here is 3.372%. Rounded, it would be 3.4% or 0.034. Okay, actually 3.4%, or as a decimal 0.034. Or you could say, I want to find the probability of being above 1.83 in a standard normal distribution where the mean is 0 and the standard deviation is 1. I want the upper tail and I want it to be above the z-score 1.83. So it's basically the same value. Rounded, it's 3.4%, or as a decimal 0.034. Okay, so here are both of those. When I stop sharing the screen, you'll be able to see that. So here's the first one. I copied and pasted the picture into my work. So if the mean was 130 and the standard deviation is 12.03, you do the upper tail above 152, you can see it's roughly 3.4%, or as a decimal 0.034 is a probability. Or if you do the same problem as a standard normal, where the mean is 0 and the standard deviation is 1. Again, you want the upper tail and you want to be above the z-score 1.83. And you get the same value, approximately 3.4% or 0.034 as a decimal. Okay.